Greetings, everybody. I'm Dave Reed with the Wilderness Workshop. Welcome to Naturalist Nights. Naturalist Nights, many of you probably know, is a partnership of the Wilderness Workshop and ACES and Roaring Fork Audubon. And our three groups bring speakers from outside of the valley and some inside the valley, 12 consecutive weeks in the wintertime. And we have, oh, there we are. It's sponsored, the slide will come up in a minute. We have sponsors that I really want to call out for you because they are the ones that make it possible for Grassroots TV back there to video this. That's why, there we are. That's why we've got the lights and I've got the microphone. In that way we can record these and then put them on the website, and Grassroots TV can put them in rotation on broadcast on Channel 12, and lots of people can see them. So thanks to those sponsors who make that possible. So today we have Andrea Holland from the White River National Forest. She's, we lost it. She's the air resource specialist with the forest and is also in charge of the water rights program on the forest. My organization, the Wilderness Workshop, has been working with Andrea for, I think, probably the whole 20 years that she's been here on the forest, because we have this great partnership on wilderness monitoring, and the air monitoring program was the original piece of that. It's since been expanded to include water and weeds, but air monitoring has been the backbone of that all along. And Andrea is going to tell you about that. I also want to call out Dave Ritchie in the back there. He is our air and water and wilderness monitor for the Wilderness Workshop. He works closely with Andrea, and I bet if you have questions afterwards, you can ask not only Andrea, but Dave. So, Andrea.
Great. Thank you so much, Dave. Thanks. So I have to get out of here and find my presentation here, and then we can get started. I am really excited to be here tonight. It is my pleasure to share with you what I do. I've been doing this for over 20 years. Here we go, from the beginning. Here we go. Here we are. Anyway, thanks so much for coming. Before I get into the monitoring program itself, I wanted to give you guys a little bit of basis of why the Forest Service is involved with air quality monitoring. After all, it's the Forest Service. We manage trees. Oh yeah, we manage cattle, and we manage, now we're in oil and gas, and we're now a multi-agency, multi-use. Air quality is kind of a new guy on the block. So the Clean Air Act was passed in 1970, and Congress established national ambient air quality standards. We call them NAAQS, for standards to protect public health and public welfare. And it's up to the state and it's up to the EPA to make sure that those standards are adhered to. In 1977, the Clean Air Act was amended, and Congress established two classes, essentially. Class 1, which were wilderness areas and national parks and national wildlife refuge centers, areas. And these areas Congress saw as worthy of protecting their pristine air quality. So those are Class 1, and the rest of the country is essentially Class 2. We still have to comply with the NAAQS, but we were tasked as federal land managers to affirmatively protect the air quality related values. Visibility is something Congress specifically mentioned in the Clean Air Act Amendment in 1977, but they also knew that there were other resources out there that could be impacted by adverse impacts from air pollution. And so hence our involvement in air resources management began actually probably in the early 80s. So we're the new guys on the block. The other act that was passed that supports the air resource monitoring program, and I'm going to go in just the monitoring program that has to deal with our Class 1 wilderness areas on the forest. It is the Wilderness Act, and essentially the purpose of wilderness was to leave it untrammeled by man and also protect and manage it to preserve the natural conditions. So we were tasked with determining what were air quality related values. And visibility, of course, was a given. But essentially it was a smorgasbord of everything that can be impacted by air pollution. Biological, it could be aquatic resources, it could be plants. Physical, it could be water quality, soil resources. Cultural, rock art is vulnerable to acid deposition or acid rain, just eating away the rock art sooner than time would allow. So the White River National Forest monitoring program currently involves visibility, and I'll go into each of these programs in more detail in just a bit. We're looking at lake water chemistry. Those are sensitive, high elevation, we call them headwaters lakes. We found, and I guess I need to back up, with our air quality related values, we needed to find sensitive indicators. And so our indicators that we chose were the high elevation lakes. And basically that was how they responded to acid deposition. We also want to know what is being deposited on the landscape. And so we've got two programs that we rely on as far as getting the information. National Acid Deposition Program, it's a nationwide program. And then the USGS has a Snowpack Chemistry program along the spine of the Rockies from Montana down to New Mexico. We're also looking at lichens. They're not plants. They're kind of a combination of algae and fungi, but they're very, very sensitive to air pollution. They're bioaccumulators, so they hold in everything that they have, and more sensitive species will disappear in greater air pollution. In the worse the air pollution it is, the less your sensitive species begin to disappear. So that was something we identified early on to monitor. And then the newer one that we're monitoring, we began looking at ozone in 2006. And ozone is it's a pollutant that affects humans, but in terms of the Forest Service, our concern is how ozone affects plants. Because plants they have lungs too, and they're just as sensitive as we are, and sometimes, in some cases, more sensitive. This is just a schematic of where our monitoring sites are. We'll start on the lower right, the wilderness lakes. We've got 10 lakes that we're looking at in the Eagle's Nest, Holy Cross, Maroon Bells, and Collegiate Peaks Wilderness. And then the USGS up in the Flat Tops has a couple lakes that they're also looking at lake chemistry. USGS also has their snow chemistry sites. They have one at Ripple Creek Pass and then one at the top of Sunlight Peak. National Acid Deposition Program, we have two monitors, one at Sunlight Peak and then one at near the base of Sunlight Mountain Ski Resort. Our lichens, we've got plots that were established in 1982 in the Flat Tops Wilderness. And then our visibility monitoring sites, we have one that's been up at Ajax for the last decade, and a newer one that was established in 2011 close to the Flat Tops. And the reason why I established that one is because that area there is less than 50 miles. I think it's like 25 miles of the Piceance Basin. And there's some concerns there because that is one of our, that's one of the areas that is slated to be developed, highly developed for natural gas. So, we don't just monitor to have fun, although I like monitoring, but we do have to have a purpose. We have to have some objective in our monitoring. And so we want to know what are our air quality related values. We want to get to know them. What's normal. So we want to develop baseline conditions, and from those baseline conditions we can determine trends, whether there's a trend, a good trend in terms of their health or a downward trend. And in some cases we monitor just to make sure that we're complying with the NAAQS. The data that we're collecting, much of it now is used in modeling efforts, and most of our air quality modeling is for oil and gas development. So the numbers that we have collected are very useful in determining impacts from oil and gas, air quality impacts from oil and gas development. But models are big black boxes, and you can't just rely on a model to say yep, it's good, or yeah, it's not so good. You need to continue monitoring, and now is a critical, critical time to continue our monitoring program. It's a very big challenge in this budgetary challenge. We have I'm just hoping that we can continue the monitoring for the next 20 years. It's a big concern of mine. So let's get into, we'll start with visibility monitoring. Anybody been up at the top of Ajax and seen this really funky white building? Aha. This houses our visibility monitor, and it also houses an ozone monitor. The other site that we have is the flat top site, and a little bit different building structure, but same instrumentation. And this picture kind of gives you a little bit of a hint of what's inside. The stacks that you see, there are 4 stacks that lead to 4 filters. And every 3 days, the pumps go on and air is sucked through to these filters for 24 hours. This is a national program, and so every 3 days, it's the same 3 days throughout every single station throughout the nation. So we're, in a sense, sort of monitoring the same air at the same time, sort of, kind of. But anyway, these filters are picked up every Tuesday, and they're sent to a lab at UC Davis, and then they're analyzed for a lot of different constituents that I'll go into just a little bit. Visibility is basically affected by particles in the air. It's either going to, like ozone is colorless, so you're not going to be able to see whether ozone is in the air or not. But if you have nitrogen oxides, if you have particulate matters, sulfates, those are little particles, and they're either going to absorb light and sort of darken the sky, or they're going to scatter the light. In any case, when you're standing up at the top of Cypress, you're going to know whether or not you've got great visibility, like it's just one of those classic blue sky Colorado days, or it's impacted either by smoke or, and sometimes it could be moisture, it could be a cloud, but that is not a particle, so to speak. It's, we're able to determine whether or not the visibility is impacted either by a cloud or by particulates. But anyway, that was just to kind of give you an idea of what we're looking at. Basically, the particles are very, very tiny. They're 2.5 microns in size or smaller. So essentially, our program, we measure standard visual range. That's something that we can all relate to. How far can you see? And then we look at the components that I got into earlier, nitrogen oxides, sulfur dioxide. It's one thing to just look out from Cypress and say, man, it is so polluted, I can't see anything. But what we want to know is what is causing that? You know, what is the source of that? Because once we understand the constituents that are made up in that column of air that we've just monitored, we can go to the source, that way we're not laying out a net and making everybody reduce their emissions. We actually can understand what's going on. So the standard visual range is one measurement that we still somewhat use, and the only time I really use it is when I'm trying to explain it to the lay person, because we all can relate to how far we can see. So the picture here on the left was actually made by a computer, digitally created. So I can just plug in how far, what's the visibility going to look like if I can see 300 miles. So here we've got a 223-mile visual range on the left, and on the right is 72 miles. The graph on the right just gives you an idea of what we've been measuring, the good, the bad, and the good visibility at the top, the blue line, kind of gives you the standard visual range, and then the bottom line is the worst, the 20% worst days. It's like a little bit more than 2 months worth of bad days, the worst days. So it kind of gives you an idea. It sort of looks a little bit like we're sort of improving our visibility, which is a good thing. We want to head in that direction because we are considered, the EPA and the state consider our visibility right now slightly degraded, and so they're working on improving that. So we have more days up in the blue line and less down there in the red line. But here's how we, when we run models and when we actually do the measurements, we're looking at deciviews. A deciview is basically one deciview is a just noticeable change in visibility. On the left, you have a half a deciview, and that is pretty reflective of our best days. On the right is almost 12 deciviews, so we're talking almost 12 times a reduction in visibility. And that 12 deciview correlates with that peak. You see that top X for 2002. So this is for the 20% worst days. Anybody know what was going on in 2002 that we would have so much reduced visibility? Fire. Aha, you guys are so smart. So, and here it is. These are the graphs that you can make from the data that we collect. So the lower blue line, the lower blue box basically represents ammonium sulfate. And then the box above that, the reddish box, is ammonium nitrate. Above that, the green one is organic material, organics, and that includes smoke. Most of it is smoke. And as you can see in 2002, boy, that green box went straight up. The purple box is light absorbing carbon, very, very fine carbon material, and then the upper one is basically windblown dust. So by looking at that, you can see that ammonium sulfate plays a pretty big role in reducing our visibility. Most of that comes from coal-fired power plants. The power plants in Craig and Hayden have gone through emissions control reduction, but they're still emitting enough to impact our visibility, and so they've been targeted to kind of ratchet down and improve the emissions even more so. So these kind of graphs help us, because otherwise we would just say, oh, visibility is bad, we should go after something or everything. We can't control fire so much right now, but it is helpful to know how that plays a role in our visibility data. This is a map. The black dots are all the improved sites that existed in 2008. And actually, we've got quite a few more in 2013. Most of them were set up in Class 1 areas, in national parks and for wilderness areas. But cities are now adopting this monitoring system for themselves, for the same reason, to just understand what's in that air. As you can see, we have some of the best air quality in the nation. Yay. The reason is because we're high elevation and we have such dry air. The East Coast is not so fortunate. They've got quite a bit of pollution, but what happens is when nitrogen oxides and sulfates go up in the air, there's a lot of humidity back there, and the humidity mixed in with these particles basically magnifies the impacts to visibility. And that's why you see those red areas where the visibility is not so good back east. So I'll go on to talk about lichens a little bit. This is a sensitive species on the left. It's called an Usnea laponica. Back in 1982, Mason Hale from the Smithsonian set up a number of plots around this Flat Tops Wilderness. And the idea was to inventory what was there so that in the future we could know whether or not there was a change in the species, whether or not we were losing those sensitive species or not. But what is more useful is you can take that little piece of lichen, you can take it back to the lab and analyze it for a number of elements. And so that we've gone and revisited those sites in 1992 and again more recently in 2008. That's just a picture of where the plots are. And this is what we've seen so far. A reduction in copper, likely due to the emissions control at the Kennecott copper mine outside of Salt Lake City. Reduction in lead, that had a lot to do with taking the lead out of gasoline. We've seen some elevated levels in nickel and arsenic, nothing to be too concerned about, but it is something to watch over. Sources of those are coal-fired power plants, wildfires, any kind of fuel combustion. But overall, Larry St. Clair, who did the report for us, he's from BYU, the lichenologist from there, and he feels that air quality right now in the wilderness is pretty good. So that's worth hanging on to, and hopefully we can keep it that way. Acid deposition, The National Acid Deposition Program is basically, it was set up and established in the late 80s, and it consists of a bucket, and it just collects precipitation, snow or rain. Those buckets are collected every Tuesday and then sent to a lab in Illinois and analyzed for ammonium, for nitrate, and for sulfate, the biggies that would contribute to acid deposition. The map on the right is basically where it kind of gives you an idea of the extent of this program. And this map here gives you a closer idea of the sites in Colorado. And our two sites on the White River, this is 92 is the Sunlight site, and 08 is the Sunlight Peak site, and then 8 is the site near the base of Sunlight Ski Resort. This is a summary of the data that we've collected so far. The top blue line, aqua line, is nitrates. The bottom line is ammonium sulfate. And even though the lines indicate maybe there's a slight trend upwards, maybe it's a little flat, really, when you run the numbers through a statistical analysis, we are not seeing any statistically significant changes in either of those parameters. However, sulfate, we have seen a very significant decrease, likely due to the fact that sulfate was taken out of gasoline and diesel back in early 2000, I think 2006. And so throughout the West, we've been seeing this pattern. And I want you to remember this, because we're gonna get back to this a little later. The Snowpack Chemistry site basically is a USGS program that we partner with them on. And George Ingersoll is in the pit on the left. And what he's done, he's got a really cool job. In the springtime, he just gets in his truck and he digs snow pits from the New Mexico, all along the Rocky Mountain spine to Colorado. And he collects the snow all the way from the top to the bottom, has that analyzed in the lab, and is basically looking at the same constituents, the sulfate, the ammonium, and the nitrate. I just thought I'd point out the picture on the right. You can actually see, can you see those layers of soil? Those are dust events. We've just been picking those up lately, and you've probably, you've been seeing a lot of press on that as well. So it's interesting. We usually try to get up there March and April, so we don't get all the dust events, but I think we've got that represents about four events right there. I've seen actually 7 or more. I just went over that. But essentially what George has done is he's compared his data with the National Acid Deposition Program. He has a lot more Snowpack Chemistry sites than the NADP has bucket sites. So he basically fills in the gap. And what he's shown, essentially what these charts are showing is that with the NADP program, they're not seeing a lot of significant differences in the ammonium or the nitrate. Actually, maybe even a decrease. These are our sites right here, our 2 sites. So we're sort of we're considered Southern Rockies. However, and we have the same trend for sulfate, both between the NADP and George's program. But George has seen a difference in trends for nitrate and ammonium. He's seeing an upward trend overall in the Rockies. And likely this is due to the fact that the snowpack is collecting not only the snow, but it's collecting what's falling out of the air. And so that's probably the difference. So his might be giving us a more complete picture of what's going on out there. This falls right into our lake chemistry study. This is a picture of Brooklyn Lake, which is in the Collegiate Peaks area. It lies about 12,000 feet. I ran some statistics a while back. We look at cations and anions, and I'm just giving you a real summary, real basic summary, the nitrate and the sulfate. Again, the two things we're looking at in terms of acid deposition. As you can see, in all the lakes that we monitor, and that's in all the way through the Flat Tops, Holy Cross, Eagle's Nest, Maroon Bells, and Capitol, we're not seeing a lot of trends in the nitrate. But we are seeing a very interesting trend upwards of sulfate. Only a few of the lakes are seeing a downward trend. This was very puzzling for me. It wasn't computing, because if there's deposition, if the sulfate deposition is decreasing, why am I seeing an increase in sulfate in our lakes? It took me a while, and I finally found another person who was seeing, she was scratching her head about this too, Elisa Mast from the USGS, and she had some lakes down in the San Juans. So when I told her what I was seeing, she just looked at me and went, wow, you've expanded my data set. This is pretty cool. So just to give you an idea, this is Tabor Lake, another lake that we monitor in the Collegiate Peaks. But look at this. This is sulfate. We started in 1991, and basically this is our baseline. Pretty, it's pretty even. There's ups and downs because nature is never static. There's some, dynamics going on. And then all of a sudden, right around 2002, it just shot up. So Elisa spent a lot of time puzzling over this. She had some hypotheses, and this is what she came up with. She noticed there was a commonality with the lakes that were showing high sulfate trends, increasing sulfate trends. Many of these lakes lie within the Colorado mineral belt. And in that Colorado mineral belt is pyrite. Usually you're going to find pyrite, which is iron sulfate. It's a very unstable rock, and when it's exposed to air and water, it'll break down and it'll dissolve into the water. So this is so that's good information. But what was causing the increase in sulfate? Global climate change. We are seeing earlier snowmelt, and so there's a lot more contact with the water and the rock, and so there's a lot more dissolving of the pyrite into the water. It's a theory, we don't know for sure, but it's pointing that way. We weren't seeing this trend outside the Colorado mineral belt in the Flat Tops or down in the lakes in the Weminuche. So it's a pretty plausible theory. Okay, so we're moving into ozone. So you need NOx, you need volatile organic carbons, and you need sunlight to make ozone. We've heard about the ozone layer. I have a cartoon that it's called the boson layer. Anyway, sorry, I just had to share that one. Basically, the ozone layer up high is protecting us from the harmful effects of UV light. Down below, though, above, ozone it occurs. It's in our air, it's a part of our atmosphere. But too much of a good thing is not so good. It's a very nasty pollutant. It really plays havoc with our lungs, and it plays havoc with vegetation. It impacts the vegetation's ability to photosynthesize. So we used to think that ozone was a summertime event only because of the sunlight part, but now we're finding out that we're also in some areas we're seeing wintertime ozone. And it's actually magnified because you have the sunlight, you got the NOx, you got the VOC, and then you've got the snow reflecting back up. So you've got sunlight coming from here, and then it's being reflected back up. So it's really, magnifying the effects in the wintertime in basins, basically. We partnered with the Rocky Mountain Research Station to assess ozone, because we're still trying to learn how this pollutant acts. It's not stable. It can move into NOx. It can move back to ozone. It's higher. Sometimes we find higher ozone levels up high. So we're trying to understand this, and basically we're also just trying to understand what are the levels and relay that back to vegetation. And there's a paper outside that I have that the Rocky Mountain Research Station put out, just a really one-pager that talks about their program and how it relates to vegetation impacts. I wanted to bring this slide up. Sometimes it helps to know what the emissions are out there to sort of provide a piece of the puzzle in understanding the impacts that you're seeing. So what I've got here I've got a graph of nitrate, which is one of the components of ozone, and of VOCs. And as you can see, and I have their comparison of 2004 and 2007. So in 2004, basically about a third of the NOx were coming from vehicle emissions and a third were coming from stationary sources, which weren't really defined until 2007, when the state said, you know, we need to, that's when oil and gas was really kicking. They said, let's break it down a little bit more. And so these green boxes basically represent oil and gas area sources and stationary sources, and then there's like a tiny bit that's not oil and gas. So most of the NOx in 2007 in Garfield County were coming from oil and gas. The same with the VOCs. Now this purple box here is, that's the natural hydrocarbons. Hydrocarbons are part of the volatile organic compounds. And that's natural, that's vegetation. So this, everything above that is basically human caused. Again, you know, here's our stationary sources in 2004, expanded quite a bit in 2007. And it kind of correlates with our data because we were seeing higher levels of ozone in 2007. We weren't monitoring in 2003. This is a summary of the data that we have so far. The red line is the standard for ozone, 75 parts per billion. The standard is written in such a way that they look at, EPA looks at the fourth highest concentration each year, and then over a 3-year period averages those, and if that average is over 75 parts per billion, then you have an exceedance of the standard. So if you look at this graph, Ajax is this line right here, and it looks like 1, 2, 3, we exceeded the ozone standard. However, like I said, ozone's a kind of a funky thing to monitor. That site that we were monitoring is at 11,000 feet. And there's a thing called, it's called stratospheric intrusion. So the ozone up high, when there's turbulence in the air mass, sometimes it dives down and will cause higher ozone levels, especially you'll see these at higher elevation sites. And those two sites, the two high readings that we got in 2009 and 2010 actually occurred in April, when we see a lot of this, the stratospheric intrusion. So we have to read this data with caution and get the bigger picture before we start running around saying it's human caused. But it is still, seriously, it's still a concern. So this is another program that we're hoping will continue. It's kind of limping along this year, and I'm hoping we can find some benefactor that will help us continue the program in the next 20 years. So basically, just to summarize, visibility is pretty good, but it's still degraded, and we are working on improving that, we being pretty much the state and the EPA. Deposition of sulfur has gone down, but the sulfate in our lakes have increased, and that's basically, we're pretty sure that's due to global climate change. Puts a little kink in our acid deposition. Trying to understand that, it's another variable we've got to consider now. And then our ozone concentrations are approaching or exceeding max in some places, whether or not it's naturally caused from the stratospheric intrusion or human caused. I want to thank our partners who, I don't know why I don't have there, but I want to mention our partners. Wilderness Workshop has been a long-time partner with us for over 20 years. They actually were the ones that helped start the Wilderness Lake program. The Thompson Divide Coalition has helped us recently in paying for our NADP program, the operation and maintenance that we need for that program. Our other partners right now are the Rocky Mountain Research Station, the USGS, and the Environmental Protection Agency. So they have been great partners, and I hope that we can continue that partnership. So thanks so much, and I can take questions now. Yes.
Hi. Can you explain again why visibility is better in high altitude areas like here versus the East Coast again?
Yes, the question was, why is the visibility better here than it is on the East Coast? And the reason is because we have dry air, and so there's not, when you have particles like nitrates and sulfates, if they react, when they combine with water, they expand. And so, and when you have your particle expands, your visibility is affected that way. So, because we have high dry, well, it doesn't matter that we're high, but it's dry. And so we're blessed with that. That's why, you know, here you can just almost see forever sometimes because the air is just so dry. But back east they're not. You know, the Smoky Mountains, there's a reason why they're named that way, and it wasn't because of air pollution. So anyone? Yes?
With your later slides, the one that showed the oil and gas emissions and volatile organic compounds, I missed where you said, where was that where were those samples taken?
Those are actually, I'm sorry, I forgot, I was talking so fast. The question is, where did the slides, where did the data come from when I showed the nitrogen oxides and the volatile organic carbons? And those are called, they're emission inventories that are performed by the state each year for each county. So those were for Garfield County. That's where that data came from. So
do they have one monitoring site or many?
No, it's not a monitoring site. Basically what they do is they inventory. They've got some idea of the amount of traffic that occurs within each county, so they count that. They do have records of the natural gas development. So they're able to just count all of those up, and they can put it in all kinds of different, the outputs can be all different, but basically anything that emits a pollutant is inventoried by the state. So it's not a monitoring effort, it's more of an inventory effort. And so there's emissions that are applied to each of those sources. So it's a way of understanding, you know, where the sources are of each pollutant. So, and it's good information, it's very helpful information in understanding the bigger picture. Way back there.
Hi. With the budget issues that you kind of referred to what extent will this monitoring be able to continue in the coming years?
Every year, it's a struggle. It really is. Because I'm competing with so many other very, very good projects. Monitoring is a really tough one because it's not an activity. We're not cleaning up campgrounds, and we're not harvesting trees, and we're not building roads or you know, doing recreation. Monitoring is a really hard one, and we're competing with very limited funds right now. Everyone is. So yeah, so it's an annual struggle. And I'm sorry, I probably didn't repeat that question, but the question was, it had to do with funding. Gary?
With the oil and gas development in the whole state of Colorado, but also in this area, it seems like monitoring should be at a very high priority.
Yeah,
It
that,
shouldn't be something that's cut because we're all concerned about good data and making sure that they're meeting their standards and so forth.
the statement was, monitoring is important, it shouldn't be cut because we want to make sure we're meeting the standards, and yeah, I agree.
To go back to the slide that showed the separation that you were talking about.
Oh, I can try
Since
and,
that's not monitoring it, that's just,
That's-
these are the potentials. So the size of the graph between 2009 and 2011 went way up, but that doesn't mean that it's attributed to
any ozone.
increase.
Any increase. But, you know, I have to say that I was looking at, the question is, you know, basically, when we look at an emissions inventory, how does that relate to actual monitoring data? And if we had monitoring data, we'd have a bigger picture. But in 2003, there was no ozone monitoring going on in Garfield County, either by the Forest Service or by the county or the state. So in 2007, even then, the Forest Service had just begun monitoring ozone. But it's a very useful tool in the future because now Garfield County has an ozone monitor, And we've got, I think, 6 monitors set out. So when you look at the emissions inventory and you look at our data, you try to see, are there some correlations in that? Air quality is a very difficult constituent to monitor because there's no boundaries really. It's just kind of floating out there. And so whatever information we can have to get a better understanding of what's going on, so then we can target the emission source and improve the air quality. That's basically our goal. We work with the state and we work with the EPA in protecting the air quality in our wilderness areas. So yes.
So for those of us who talk to the public about air quality in this area, I know that for us naturalists that work here for ACES, we take people through areas where there are almost like curtains of Usnea trees, and we love to talk to people about how pure the air is here, and that's why there's so much Usnea out there. Are there any key points that you would like us to relate to the public in terms of kind of cause and effect that would impact the quality of our air and maybe change what they might see in the future in those areas?
Thank you. The question was, as for naturalists, what kind of information can we provide the naturalist to cinch in a little bit of information about the vulnerability of lichen to air pollution. And I would love to get with you later on that one, because I have some ideas and I can actually point you in the direction of some folks that actually could really, I'm seeing a hand raised. Are you a lichenologist back there?
I was liking that.
You're liking the lichens. But thank you. That kind of getting the message out would be wonderful, and I would love to work with you on that.
Okay.
So you're with ACES?
Yeah.
Super. All right, let's get together afterwards.
Okay.
Yes.
You were talking about the high-level ozone layer as opposed to the ozone and that's a good, how high up is that layer? I don't think I heard.
It depends. That's a really good question. How high is the ozone layer, the upper ozone layer? And I couldn't tell you. It's above where we live. It's above, we're in the troposphere. So we're...
You said because it can come down clear to 11,000 feet.
Yes.
And I thought that it was like miles and miles up there. I mean,
Oh, it is.
30 miles,
Yeah.
are you talking?
I would suggest you Google that because I can't tell you. I just know that there's a number in my head, and I'm afraid that if I give it, usually I'm right, but I don't want to say anything and then be absolutely totally wrong. But it's up there, and it's a thicker layer. It's a stratosphere. I think we've got like several layers in the Earth, but it doesn't mean that it doesn't mix now and then down here with us. Yeah. Yes.
On one of your earlier slides, you showed a big wildfire year in 2002.
Mm-hmm.
How did last year compare to a big year like 2002?
The question was, how did last year compare to in terms of visibility? And I wish I could answer that question for you because I'm as curious as you are. It takes a year for UC Davis to analyze that data and publish it. They're getting better at it, but at this point, I don't know because it's still, the filters haven't all been analyzed. So I update as soon as I get that information, but I don't have it right now. So, yes.
Another funding question.
Yikes.
It seems like your job is being made more difficult, or more labor is being required because of the oil and gas development. Or let's just say what you do is more important because of that. Does any funding flow from the oil and gas industry to your department?
The question was, in terms of funding, does the oil and gas industry support air quality monitoring with the Forest Service. And at this point, no. I can't, I just stunned everybody. So, oh, more questions?
What are your apprehensions and concerns about the future for air quality in this area?
What are my apprehensions and concerns about the future of air quality in this area? I think as this area develops, and it's not just going to be oil and gas, it's going to be our traffic, it's going to be the population areas that are upwind of us, and it's going to be acid deposition. Perhaps they are predicting, the Western Regional Air Partnership is actually, they're looking at models and everything and seeing that, sulfate, that downward trend in sulfate might go back up again. And the nitrates, of course, may start rising. Those are concerns, definitely. The hope is that we can stay on top of that, and that the state and the EPA can stay on top of that, and the technology can improve so that we can see the growth, we can see the oil and gas development which this country needs. I don't think there's a question on that. But to see it done in a responsible way where we don't have, where the emissions are reduced and we're not seeing adverse impacts. That's the hope, is that technology will keep up with the growth that we're seeing in this area.
Well, thank you, Andrea.
Okay, thank you, guys.
I'll just say one last thing. Next week, we have Eric Odell from the Colorado Parks and Wildlife talking about wolverines. The title is, Can Colorado Contribute to Wolverine Conservation in the Face of Climate Change? So I hope you can make it to that.